streak. We've talked about cleavage, talked about hardness. Yeah, no worries. Luster, color. And color is one of the worst ways to ID a mineral. it's a good way to identify if you've used all the other properties. And sometimes you can just, some minerals are just that obvious. Like amethyst is just a very, very obvious mineral. One, because of the hexagonal structure. Two, because of its color. It's it's just very obvious. And I know that some people do use it, but purple is not the best way ever to identify amethyst because there are a lot of other minerals that can be purple. Lepidolite, fluorite. I don't know. I'm just looking at what I have on my desk. Fluorite can be a ton of colors. There's even rainbow fluorite, which is actually sold, and it's very, very pretty. Turquoise is a mineral, yes, Weaseful. It typically forms in very massive chunks. Although it does have a chemical system and form that it can form, it typically just... there's azurite in this mineral as well. If you're looking at the tan part of the mineral, that's not the one we're talking about. We're talking about the red portion here, which is why I have the microscope camera out to take a look at that. The habit it can form, the way that the shape that the mineral can grow typically can be acicular or needle-like. It can form in little, tufts, little acicular tufts. I've seen like radiating tufts of all these tiny little needles, and it looks kind of fuzzy. I think I can find a picture of it. I think there's one on Mindat. Prismatic crystals, which also I've seen images of. And I don't know how these minerals are going to look, but they are going to look quite fantastic. And then occasionally as massive coatings just on minerals, which is kind of what this one looks like to the naked eye. It just looks like a red coating on there. You can't really see any individual crystals. You can't see light reflecting off of any individual minerals there. It's difficult to make out even the luster. Like you can't really tell. To me, it's just kind of dull. But it is... There's a couple of tiny sparkles in there, so we might be able to see a couple of mineral shapes on there, so I'm hoping to see that. But the blue is the blue is azurite. The blue is azurite, and the red is erythrite, which I think is a very, very cool spelled mineral. The diaphanate. The diaphanate is basically how does the light reflect, transmit, or absorb in the mineral? In this case, on the atomic scale, and this really has to do with the atomic scale again, because this mineral, for example, is transparent, translucent. It's not an opaque mineral because on the thin section scale, which is technically about 30 microns thick, you can actually see right through this mineral. With metallic minerals, you cannot. So this one, this is galena. No matter how thin I slice this one, I won't be able to see through it. So this is opaque. And it's hard to tell this one with the naked eye. But I do like to include it because I think it's cool. I think that optical properties in minerals are fascinating to me. And I hope that you find them fascinating too. Tenacity. Tenacity, again, I did mention this earlier. It's the way the mineral actually deforms under stress. AKA, well, pressure. Let's say you try to squish it with your fingers. That would be a type of stress. You're putting energy on it. You're trying to squish it. And in some minerals, in the case of some minerals, you could probably actually squish them. Talc would be one. It's only got a hardness of 1. You can literally scrape it with your nail. In fact, did you know that your nail is about a hardness of 2.5? So you can actually use your fingernail that you can't see because it's in my glove. You can actually use your fingernail to test the hardness of certain minerals. Now, most are going to be harder than your nail, but some will not. All right. So the tenacity, going back to the tenacity, how does this mineral deform? It's got a sectile tenacity. So you can cut this one with a knife. It's one of the very few minerals like selenite that you can actually cut with a knife. That is what sectile means. That is how it can deform. And it's so cool and weird. Here's another really, really weird and interesting thing about this mineral specifically. There is on one of the planes of this mineral, and I need to go over crystal geometry, crystallography with you at some point so you understand more of what this means. You see 0, 1, 0. That refers to a specific plane in the mineral. There's one direction in that mineral where the planes are actually flexible. So there's 2 different types of tenacity in this mineral. I think it's so cool. Additionally, there actually are 2 hardnesses. You could see that 1.5 and 2.5. It varies based on the direction or the rotation of the mineral that you're looking at. Which plane are you looking at? Different planes of this mineral, like other minerals, like kyanite, for example, have different hardnesses. Kyanite has, I think, a hardness of 7 along the perpendicular to the C-axis and a hardness of 4 parallel to the C-axis, if I remember correctly off the top of my head. I might have the number slightly off, but there's a pretty distinct difference in hardness in that mineral. And in this mineral too. I mean, it's only a 1.5 to a 2.5. It's not extreme as kyanite is, but it's still really cool, I think. I did actually already cover what subvitreous means. Subvitreous is just how shiny it is. It's again going back to the luster. So waxy, pearly, dull. That's another thing about this mineral that's so cool. There's a specific plane that actually has a pearly luster, a different luster than the rest of the minerals. And this, it blows me away. I think it's very, very cool. I think it's very, very, very cool. Yeah, it just has to do with how shiny it is. So, and that can be quantified. You can actually look at that via the index of refraction or the refractive index. And it's the speed of light in a vacuum divided by the speed of light through whatever mineral you're studying. And then that number, usually between 1.5 to 2, is the index or refractive index. But you can use terms like vitreous, earthy, dull, pearly, subvitreous, adamantine, metallic, submetallic as words to describe that if you don't have the index of refraction. And typically, the index of refraction isn't used. Like, we don't memorize the numbers for each of the minerals. I've never taught a class that we've done that, and I've never been in a class where we did that. But I find the index of refraction to be really cool. And I personally prefer to use that. It's just hard sometimes because minerals are so varying. Individual minerals can be so varying. You can have quartz that's kind of dull relative to vitreous quartz. I mean, it can vary from even within the same mineral. Yes, Miller indices. You probably needed to read that quite a while ago. Oh, this is fantastic on Mindat. Great. I'm glad people are interested in the crystallography of minerals. It's very interesting to me, but some people like to avoid it. I personally love the chemistry of minerals, I think, more than the crystallography, but the crystallography just offers more ways to ID minerals, not if you don't have microscopes available. And it's exceptionally helpful if you can see crystal planes. The problem is a lot of minerals don't show crystal planes, which is why electron microscopes are exceptionally beneficial into IDing things because, well, sometimes all you have is some blue and red splotches like the mineral that I have, right? So it's hard to figure out, well, what the hell is that? What the hell is that? All I can see are colors, right? With my hand lens, I might be able to see a little bit more, but I don't. I mean, if you had a big outcrop of this, I mean, you could then, of course, pulverize some of it and determine its hardness and its streak and other things. But using the Miller indices in this case would be impossible, which is probably why it's not taught as much. We've talked about diaphanate, tenacity, the crystal system classification. Where does it occur? Where can you find these things? I did mention that it's one of the indicators for iron ore, specifically nickel and iron. Not iron ore, just cobalt and just ores. It is an indicator for specific ores, specifically nickel and cobalt. Not iron, nickel and cobalt. I did read one paper that suggested it was also an indicator of native silver. I'm not sure about that, though. Not 100% on that one. This mineral, yeah, so specifically it's an indicator for ores like nickel and cobalt, like I said, but specifically in oxidized zones. So you need that oxidation. So it, which is actually pretty common with a lot of pretty minerals. I think it's very similar with dioptase, one of my personal favorites. This is actually a mineral with chromium in it. It's called fuchsite, and it is a mica. And all those tiny little sparkles you see are individual little planes or little tiny mineral surfaces that you're seeing. This mineral it only has one plane of cleavage like all of the other micas. It's called basal cleavage, and it looks more like this guy. This is muscovite. So you can see that one plane right there, and this is a very, very flexible mineral. You can bend it. So that is the tenacity. I'm putting stress on this mineral, right? I'm bending it, and it can bend there and it can change positions. It doesn't just stay in that position. And the luster, I'd say it's maybe pearly to subvitreous. It's pretty shiny. This is from a kit, which is why there's a number on it. But muscovite is only one of many micas, and it's actually pretty easy to identify because of the cleavage, literally because of the basal cleavage. It's very distinct in muscovite, biotite, other micas, that lepidolite, muscovite, biotite, fuchsite. Oh my goodness. I don't know. There's too many. So many. Put this there. Oh, it's a member of the Vivianite group, which I don't have a sample of, and there are other minerals that it's a part of. But basically, it does form a solid solution series, at least with, I think, Annabergite. Yeah, Annabergite and Erythrite series. It does form a solid solution series. Thank you for the follow. So nickel to cobalt. So there's an exchange between the two, those cation slots, right? That there's probably a sample of something somewhere with a little bit of nickel and cobalt. I don't know where the immiscibility gap is, but it's really cool. So this is Annabergite, which is just glorious looking. Yeah, they're both monoclinic as erythrite. So this is a very, very zoomed in picture. One of the things I don't like about Mindad is they don't always put a image for scale. That's quartz. You can see its hexagonal shape. Anyway, they don't always include a scale bar or something for scale, but the images are just gorgeous. All right, so erythrite is the mineral in question, and like I said, it can be a magenta, it can be like a pale pinkish, but this kind of red magenta seems to be the most common, and that's basically the color of the one that I have. So I want to show you with this camera now, the big one. I want to see now what this erythrite looks like. The blue again is the blue is the azurite, and those red crystals, oh my God, those are beautiful. That red is the erythrite. I want to see if we can see any of the shapes. I don't know what the ground mass is here, the whitish yellow stuff. Ooh. Here's a nice crystal. All right, I'm going to go over here. Serpentine is very nice as well. I agree. Serpentinite is the metamorphic variety, which is actually pretty neat too. It's a very soft mineral, so I don't want to break it. The blue is really pretty against it. There was one cluster that I saw. Is it this one? Do you see? Oh my God, you can actually see those individual little... They do really radiate out in those little, almost spherical shapes. Okay, that's the one right there I wanted to look at, right there. This guy. That's really pretty. You can see some nice light reflectance there. I don't honestly know if that's subvitreous or not. Let's try to zoom in. Sometimes I can zoom in a bit. Look at that, Hikari. This was actually a gift to me from Hikari. So I just wanted to really show this one off for her. Holy shit. This is fantastic. Again, this is erythrite, the mineral in the screen. There we go. It's really hard to do this with both my hands, I'm not gonna lie. I don't have a stage that isn't moving. That light right off that one plane right there is insane. Yes, science streams, typically. Blue is oftentimes or green. Green doesn't always occur because of copper, though. In the case of malachite, it is copper. In the case of fuchsite, it's chromium. And I know I think vanadium can also be green, turn things green. I don't remember all of them off the top of my head. Good God, this is so cool. Look at this, dude. I don't know. It might be the pearly plane. It's hard to say. It's hard to say because I can't see the full crystal structure. It makes it a little bit more difficult. Let's look over here. So you've got some smaller clusters over here. Ooh, there's a nice... No. Right there. It's hard to say because I can't see the entire crystal three-dimensionally. I can just see one angle of it because of how tiny it is. Ooh, that's a nice pale pink color. It's not always bright red. That blue azurite, though, is quite nice, too. In fact, I can look at my other azurite sample. Yeah, but look at... That is actually very... Oh, wow. Look at that. That actually goes from pale pink to that bright red. And this mineral is pleochroic, so in different orientations, it does display different colors. And that, again, goes down to the chemistry. Yeah, that's very... I would call that pearly. That's very pearly. That's probably the pearly. The pearly plane. Exactly, that's what pleochroism is, Hikari. The changes of color depending on orientation. All right, let's look at this azurite over here. You know what? I want to look at my other azurite. So this is that sparkly version or variety of of azurite that I have. I'm gonna drool right now. Oh man, there's some dust on this one. I need to clean this one off. But damn, look at those crystals. Ooh. That's some nice azurite. And this does have copper in it. That's just beautiful. Holy shit. I'm fascinated and I love it. Maybe I did think it was for a good time, friend. It was a good time, friend. I don't know what all this other stuff is. Probably, I don't know. Probably, I don't know. The azurite is a copper carbonate. I don't know exactly how much carbonate relative to the copper there is, but it's the same as malachite, and that it's both. They're both, yeah, but they're both copper carbonates, so they both have copper and carbonate, which is why it'll react with HCl. I can't get over this erythrite. Again, erythrite is the red mineral in question, not the blue. The blue is azurite. The rest, I don't know. Might be some quartz. I don't know.